In this video, we're going to demonstrate the use of Ansys products in a product design scenario. The goal of this demonstration is to add a pocket to the back of this bicycle crank arm that will accept electronics and strain gauges that can measure the force applied to the pedals. The first thing we need to do is add a pocket to the back side of the crank arm. In order to do this, I'm going to use a beta feature in Ansys 2020 R1 that allows us to record the steps that we take inside a space claim. To do that, I go into the Space Claim Options, Advanced tab, and turn on Beta Features. Now this feature will be fully released in Ansys 2020 R2. And then I'm going to create a sketch. The sketch will start as a simple rectangle, and I'm going to use the provided plane as the sketch plane. I'm just going to draw a rectangle and add some dimensions. I can then double click on these dimensions and edit their values. We'll start out with a pocket that's 1 inch long, 3/4 of an inch high, and 2.5 inches away from the axis of the bottom bracket. I'm going to switch over to 3D mode. Switching out of sketch mode changes our sketch into a surface. And you can see we now have a listing over in the feature tracking tree of a sketch. Inside of this window, I can then modify any of the dimensions that we created. For instance, the first thing I want to do is take this height dimension and turn it into a parameter by clicking this P button. You can see we now have a parameter listed down in the parameter window. And I can use this parameter in formulas inside these other dimensions. So for example, dimension 2 centers this rectangle on the crank arm. So I'm going to go ahead and edit this dimension so that it is 1/2 of parameter 1, P1 divided by 2. Once I've made my changes, I can go ahead and click this play button, and it will recreate everything in this tree, changing the dimensions to match what were entered. We'll now use this surface body to create a cavity inside of the crank arm. If we go to the Design tab, we can then use the Pull tool, select the surface we want to pull, and on the pop-up menu, we're going to select the Cut operation, and then we're going to drag our surface body down into the crank arm. You can see the farther we drag it, the deeper the cut goes. So I'm going to press spacebar. This locks in the current depth and allows me to type in a number manually, and I'm going to make that 0.65 inches. This will be the starting depth for our pocket. So I'm going to change the shape of this pocket a little bit, and I'm going to stay in the Pull tool to do that. And I'm going to select 3 of the faces of the walls of this pocket. I will then right-click on the pocket and select Full Round. I will do the same thing on the opposite side. And finally, I want to add a fillet radius to the bottom of the pocket. If I double-click on an edge, Space Claim will automatically select all tangent edges, and it's still in the Pull tool. I can drag that edge to add a radius. I'll press the space bar and make that radius 0.02 inches. The last thing we want to do in the geometry is add another parameter. And then I'm going to expand the extrude face item and take the distance parameter, this is the depth of our extrusion, and turn that into a parameter. So now we have 2 parameters that we're going to use later in our Design Explorer study. With our geometry modified, we now want to load it into Ansys Mechanical for analysis. I've already opened up the Ansys Workbench project page, and we're going to drag and drop a static structural analysis into our project schematic. We will then link our geometry branch to the geometry we created in Space Claim. I will then refresh the model to load that geometry into Ansys Mechanical. Once that geometry is loaded, you can see we have a parameter set that's been included. If I open up the parameter set, you can see we now have P1 and P2 that we created inside of Space Clean. We will then launch Mechanical by double-clicking on Setup. Now that our geometry is inside of Mechanical, we will add loads and boundary conditions and run an analysis. The first thing we want to do is add a fix support here at the bottom bracket. So we'll select that face, click the fix support button, and then we want to add a force where the pedal goes. We want that force to be in the Y directions. We're going to take a guess and say it's 500 pounds. We will also need to define the material of this crank arm. By default, it's going to be set to structural steel. We want this crank arm to be made out of aluminum, so under Materials, we'll click on the Materials branch and we can type in aluminum. Now you can see with the addition of Granta to the Ansys family, we have a massively expanded material database inside of Ansys Mechanical. Previously we only had one form of aluminum, now we have a whole lot. So we're going to search for a specific grade of aluminum. I'm going to do 6061. You can see it here. If we click on that, our material properties will be listed. And if we click the plus button, it will be added to our analysis. So now if I expand the materials branch, you can see we have 6061 there. I will go ahead and apply that to our crank arm. The last thing we need to do in the model setup is to add some mesh refinement. If I generate the default mesh here, zoom in on our pocket, you can see we've only got one element through the thickness of these walls. And since we want to get a reasonable estimate of the strain in these locations to add in a strain gauge, we're going to want to add more elements there. So I'm going to go ahead and select the walls of this pocket and add in an element sizing. That size will be 0.02 inches. And we will regenerate the mesh. And now you can see we've got 2 to 3 elements through the wall thickness at its thinnest, which should be more than sufficient for what we need. We will also need to add some result items to our solution tree. So for results, we will likely want to see a total deformation as well as equivalent stress. Now for the equivalent stress, we want to see it mainly in this pocket. We're not necessarily concerned with the rest of the design. So we are going to change the scoping from all bodies to just certain faces. So we're going to select the walls of the pocket and scope the geometry there. And we also want to add strain. So we're going to add strain in the Y direction to those same walls. With that, our model is set up and ready to run. With the solution complete, we can take a look at our total deformation, and we can create an animation of that displacement. We'll take a look at the stress in the pocket, and you can see we're about 7,000 psi with this particular pocket design. And looking at the strain on the walls, you can see we're at about 200 microstrain with a 500 pound load. So now we want to go ahead and optimize the design. We want to see what height or depth of pocket that we can do to make sure that we don't overstress the part, but still create a nice strain field for our gauges. In order to do that, I'm going to add a couple more parameters, those being output parameters, and the first is equivalent stress. So I'm going to select equivalent stress, scroll down here to my results section, and make this maximum number a parameter, and do the same thing for the elastic strain. With those parameters defined, we'll move this design over into Ansys Design Explorer. The optimization analysis is found under the Design Exploration section of the toolbox. We want to run a direct optimization on our crank arm, so we're going to drag and drop a direct optimization underneath the parameter set. There are several design exploration tools included in Design Explorer. Besides optimization, there is also parameter correlation. This allows you to take a whole bunch of parameters in your FEA model and find out which ones are really important for your output parameters. And those are the ones you would want to include into your optimization analysis. With our study, we've only got 2 parameters and we already know they're important, so we don't need to run that one. You can also do response surface optimization, and in this case, Ansys will create a mathematical representation of your entire design space, and not just look at discrete points. And then there's the Six Sigma analysis, which can determine how many parts per million are expected to not meet your design criteria. For this type of analysis, you will enter in a statistical distribution for each parameter. For now, we're going to focus on our design optimization. So I'm going to go ahead and open up Design Explorer. And inside of Design Explorer, we have to enter a few items. The first one is under our optimization, we have to tell it what we want to optimize. In this case, we want to try to minimize our equivalent stress. So we want the stress to be small, and we're going to add in a constraint that we want to have it less than 7,000 psi. And we also want to make sure our strain values don't get so small we can't measure them. So we're going to go ahead and select a strain constraint to have it larger than 100 microstrain. We then need to tell Ansys how our parameters can vary. So I'm going to go ahead and select our height dimension, and we're going to create a lower bound of a 1/2 inch and an upper bound of 3/4 inches. For the depth, we're going to set the lower bound at -0.9 and the upper bound at -0.64. With the optimization defined, we can run the analysis by clicking the Update button. This analysis will take 15 to 20 minutes to solve on my laptop, so I'm going to go ahead and stop the solution here and open up a solved copy. When the solve is complete, Ansys will display the results for each run that it made. In this case, you can see we did 18 solves, and we used nearly the full range for both the height and the depth that was defined at the start of the analysis. And on the right hand side, you can see the equivalent stress and the elastic strain that matches each case. Under my objectives section, if I select parameter P3, I can see the results for P3 for each run. So the red line is my maximum equivalent stress, and the dashed lines are the limits that we had set. So we wanted to try to minimize the stress to 0, but we wanted to also give it a constraint that our candidate points could not have a stress above 7,000 psi. We can also look at each parameter in the study and see what the value was for each run. Now in this case, the red line shows the height parameter for load cases 1 through 18. The blue lines on the graph show us the search range that Ansys was using at the time. So you can see at the start of the optimization, we're using the full range of 0.5 to 0.75 inches. After the first 10 runs, Ansys determined that the maximum pocket size was not where the optimum was going to be found. So it reduced the search range from 0.5 down to 0.6 inches for the remainder of the run. This helps accelerate the optimization solutions by not spending time solving cases that Ansys already knows will not be optimal. So the goal of this analysis was to find the optimum pocket depth and pocket length. If we click on candidate points, Ansys will give us the 3 best options for the optimal size. Candidate number 1, with a height of a 1/2 inch and a pocket depth of -0.64, is what Ansys believes the best choice to be. This is just a way to simplify how well that the optimization parameters were met. A 3-star rating is the best, a 3 negative sign rating would be the worst. Hopefully this short demonstration gave you a feel for how Ansys products can be used in the design of your parts. If you have any questions, I'd be happy to answer them at this time.